Welcome back to the deep dive. If you grabbed coffee, checked your bank account, maybe booked a ride this morning, chances are you were interacting with some truly massive, complex software.
Absolutely. Things like banking, healthcare, logistics. Our whole modern world basically runs on this incredibly complex code, and the old ways of building software, they just completely fall apart at that scale.
Right, it turns into digital chaos pretty much instantly.
And that chaos is exactly what we need to tackle. When systems get this big, this long-lasting, spread out everywhere, you absolutely need a structured, disciplined way to handle all those moving parts.
And that method is object-oriented analysis and design, or OAD.
That's the one.
So that's our mission for this deep dive. Unpack how OAD gives us the framework to build software that's actually reusable, maintainable, and can grow without collapsing. So let's start right at the beginning. OAD seems to split development into two key phases, right? Analysis and design. What's the difference?
Yeah, think of system analysis as the detective work. It's all about figuring out what the system needs to do. You're looking at it from the user's point of view, gathering requirements.
You get the what?
Exactly. Then, system design is more like being the architect. It's deciding how the system will actually do it, choosing the right structures, the components, how they fit together.
And OAD brings these together, but with an object-focused twist from the very start.
Precisely. It uses object principles throughout both phases.
Okay, let's unpack this. Maybe starting with why software is just so darn difficult to build in the first place. What makes it harder than, say, building a physical bridge? The physics don't change there.
That's a great comparison. Well, the sources point to about 4 core reasons. First up is the problem domain. The requirements themselves are often huge, constantly shifting, and sometimes they even contradict each other. Imagine building that bridge if gravity decided to change direction every few weeks.
Huh. Yeah, that would be a nightmare. Okay, so messy requirements, that's one.
Then there's the development process. You often got large teams, maybe spread across the globe, all trying to hit a target that keeps moving because the requirements are evolving.
Yeah.
It's tricky coordination.
The goalposts are always shifting. I get that.
The third one is maybe the sneakiest, the sheer flexibility of software. Because you can technically code almost anything. Without strict discipline, it's incredibly easy to create utter chaos. Total spaghetti.
If you can do anything, you often end up doing the wrong thing or doing it badly.
Exactly. Which ties into the fourth point. Software systems are discrete systems. They have an astronomical number of possible states, internal paths a program could take, testing every single one. It's mathematically impossible. You just can't check everything.
Wow, okay. So messy problems, messy process, too much freedom, and too many states to test. No wonder things go wrong.
And they did go wrong. This led to what people called the software crisis back in the day. Projects were chronically late, way over budget.
Or they just plain didn't work as promised.
Right. The sources mention Nairobi's IFMIS, their big financial management system. It apparently faced failure after failure, largely because the complexity just overwhelmed the design. It wasn't just bugs, it was the fundamental structure that couldn't cope, like the Wild West of coding.
So if it's that complex, how does anything complex ever get built successfully? Like, how does an app like Uber even function? The research mentions common traits of successful complex systems. Booch's attributes, right?
Yeah, thankfully successful systems do share some organizing principles. First, they almost always have a hierarchic structure. Big systems are broken down into smaller, manageable subsystems.
Like with Uber, you'd have a payments part, a maps part, a notifications part, something like that.
Exactly like that. Which brings us to another key idea. Separation of concerns. You can actually look at, say, the mapping feature without needing to understand the guts of the payment processing at the same time.
Makes sense. You can focus.
And then there's relative primitives. What seems simple on one level is actually built on complex stuff underneath. So for the main Uber app, a car might just be a basic thing on the map.
Right, an icon.
But inside that car object, it's managing GPS data, maybe engine diagnostics, driver info. It's its own little complex world.
Okay, that makes sense. Hierarchy, separation, primitives. What else? The sources mention patterns, right? We don't reinvent everything.
Oh, absolutely not. Successful systems rely heavily on common patterns. Think of things like the model view controller, MVC pattern. These are like tried and tested blueprints for organizing code.
So you're not starting from scratch each time.
Definitely not. And one more thing. Stable intermediate forms. Complex systems usually evolve. They start as something simpler that works, and then they grow and add features incrementally. Facebook wasn't built in a day, right? It started small and grew.
All right, started in a dorm room or something. Okay, so complexity is the beast, but structure helps tame it. Historically, though, before OAD really took hold, how did we try to manage things? You mentioned the Wild West, unstructured programming.
Yeah, back in the 60s, basically one giant block of code. Maybe okay for a tiny calculator program, but anything bigger. It became the infamous spaghetti code, jump anywhere, change anything, total chaos.
Impossible to maintain or understand.
Completely. So the next big step in the 70s and 80s was procedural or structured programming. This was a huge leap. It introduced the idea of breaking down problems, but crucially, it broke them down based on algorithms or steps.
So the focus was on the process, like what are the steps to calculate payroll?
Exactly. What are the steps? And this worked much better, but it had a critical weakness. The data, like say, a customer's information, was kept totally separate from the functions, the procedures that acted on it, like calculated discount.
Ah, okay. So if I needed to change how the customer data was stored, maybe add a new field?
Boom. Every single function that touched that customer data structure was suddenly at risk of breaking because that data was often just out there, globally accessible. Changing one little thing could send ripples of destruction across the whole system. Very fragile.
Fragile, brittle. I can see how that would be a nightmare for large, evolving systems.
Yeah.
So how did the object-oriented approach fix that fundamental problem, that separation?
This is the real paradigm shift. Instead of breaking things down by steps, OAD breaks things down based on concepts or things. You ask, what are the actual objects in this problem domain? A customer, an account, a product.
Okay, focus on the nouns, not just the verbs.
Kind of, yeah. And the absolute genius move was bundling the data and the behavior that acts on that data together into a single unit, the object. This bundling, this encapsulation is key. It dramatically limits that ripple effect when things change.
Right, our sources really highlight that difference. Structured analysis focus on process, tools like data flow diagrams, good for maybe simpler calculation-heavy things like payroll, whereas OAD focus on objects and their interactions, using modeling tools like UML diagrams, which are like standard blueprints for software.
The unified modeling language, yeah. Standard way to visualize object systems.
Making it much better suited for complex dynamic systems like ride-sharing apps or inventory management.
That shift really enabled the kind of software scale we see today. It just wasn't practical before.
Okay, so this OAD approach sounds powerful, but it's not just magic, right? It's built on some core principles. The sources talk about 4 main pillars.
Exactly. 4 major pillars hold up the whole object model. Abstraction, encapsulation, modularity, and hierarchy. You got to understand these 4.
All right, let's take them one by one. First up, abstraction. What's that about?
Abstraction is basically about simplifying things. It's the act of identifying the essential characteristics of something, what makes it, while deliberately ignoring all the details that aren't relevant for the current context. It gives you a clean, simplified view.
Okay, like the dashboard of my car. That's an abstraction, isn't it? It shows me speed, fuel level, the essential stuff. It hides the incredibly complex engine mechanics, how combustion actually works.
Perfect analogy. You don't need to know about piston rings to drive the car. Same in software. If you're modeling a car object, you need attributes like speed and fuel level, maybe start engine. You don't need to model the chemical reactions inside the battery.
So it reduces the mental load. You only deal with what matters right now.
Exactly. And it means you could, in theory, swap out the entire engine for a completely different type, maybe electric, without needing to change the fundamental dashboard interface, the abstraction of how fast am I going?
So it separates the what's from the how. Yeah. Very cool. Okay, pillar 1, abstraction. What's next?
Next comes encapsulation, which is often talked about alongside abstraction. Sometimes it's called information hiding. This is about protecting the internal state of an object.
Hiding the insides.
Sort of. You hide the implementation details, the data, and the complex logic, and you only expose a controlled public interface, usually a set of methods, for other parts of the system to interact with.
Like the TV remote control analogy. Yeah. The remote is the public interface.
Yeah.
I press volume up. Yeah. I don't need to know or mess with the circuitry inside the TV that actually makes the sound louder.
Exactly that. In code, imagine an account object, its actual balance variable. You make that private, hidden.
Okay.
Then you provide public methods like deposit amount or withdraw amount. All interactions must go through these controlled methods.
So you can just reach in and set the balance to whatever you want.
Precisely. And that's where the power comes in. Inside that withdraw method, before it changes the private balance, it can check rules. Is there enough money? Is the account active? It enforces the business logic and protects the data's integrity.
Okay, that makes sense for safety. But doesn't hiding the internal state, like the exact balance, make it harder to figure out what's going wrong if there's a bug? If I can't see inside, how do I debug?
That's a really common question, but it's actually the opposite. Encapsulation usually makes debugging easier. Think about it. If the balance is wrong, the only way it could have been changed is through one of those public methods, like withdraw or deposit.
So it narrows down where the problem could be. Instead of anywhere in the system touching the data, only a few specific places can.
Exactly. It localizes the potential source of errors. It forces a certain discipline.
Got it. Okay, abstraction simplifies, encapsulation protects. Pillar 3.
Modularity. This is about breaking the system down physically, dividing the program into distinct components, often classes or groups of classes called packages or modules that can ideally be developed, tested, and maintained somewhat independently.
Right, breaking the big problem into smaller, manageable chunks.
Yes, and the goal here is to create modules that have two key qualities: high cohesion and low coupling.
Okay, high cohesion. That means the stuff inside one module really belongs together, right? It has a single, clear purpose, like maybe a module just for handling file operations.
Perfect example. It does one thing well. And low coupling means that modules don't depend too heavily on the internal details of other modules. They interact through stable interfaces, those abstractions we talked about.
So if I change the internals of the file handling module, I hopefully don't break the user interface module because they're not tightly tangled together.
That's the ideal, yes. Low coupling makes the system more resilient to change. You can swap out modules more easily.
Makes sense. Build with Lego bricks, not duct tape. Okay. Abstraction, encapsulation, modularity. What's the fourth pillar?
Hierarchy. This is about organizing your abstractions, usually based on ranking or classification. The most common form of hierarchy in OOAD is inheritance.
Inheritance. That's the is a relationship, right?
Exactly. Like a savings account is a type of account. A checking account is a type of account.
So the savings account can inherit all the general properties and behaviors of an account, like having a balance, an owner, maybe a deposit method, without having to rewrite that code.
Precisely. It promotes massive code reuse. The common stuff lives in the parent account class, and the specialized classes like savings account just add their unique bits, like maybe an interest calculation method. It creates a clear structure and avoids duplication.
That seems incredibly powerful for building complex systems efficiently.
It really is. Now, those are the big four. The sources also mention some minor elements, things like typing, how strictly we define data types, concurrency, handling multiple things happening at once, and persistence, saving data long term, but often these rely heavily on the major four pillars being in place correctly.
Okay, that's a lot to digest, but I think I'm getting the picture. So, stepping back, what's the big takeaway here? What does this all mean for someone trying to grasp how modern software gets built without falling apart?
Well, the big takeaway is that OOAD provided the mental toolkit and the structural framework to finally escape the fragility of those older procedural methods by shifting the focus from scattered functions operating on exposed data
The brittle approach.
to focusing on stable, encapsulated objects that bundle data and behavior together. We gained a way to build systems that are far more reliable, much easier to scale up, and critically, much easier to maintain and change over time. That's the core win.
When we saw that with the ride-hailing app example, the objects are pretty clear. You've got riders, drivers, vehicles. And you mentioned patterns, like the factory pattern. That sounds like encapsulation in action, right? A way to create different kinds of vehicle objects, cars, bikes, whatever, without the rest of the app needing to know the nitty-gritty details of how each one is constructed.
Exactly. The factory pattern encapsulates the object creation logic. It hides the complexity, providing a simple interface to get the vehicle you need. It's a perfect example of applying these principles.
Very cool.
The source material wraps up with a really neat thought experiment, trying to model a complex real-world system like a hospital using OOAD principles.
Oh, interesting.
Yeah, so maybe a final thought for you to chew on. Think about that hospital. What are the core objects you'd probably have? Patient, doctor, nurse, appointment, maybe bill, department, lots of things.
Right.
Now pick a specific process, like admitting a new patient. Where would abstraction be used to simplify the view of that patient for the admissions desk? Where would encapsulation be vital, say, for protecting sensitive medical history or billing details? How does hierarchy play a role maybe in classifying different types of staff, doctor specialists, nurses, or different types of treatments?
So applying this OED lens isn't just for code. It's a way to think about structuring any complex system.
That's the idea. It gives you a powerful framework for analyzing complexity, whether it's digital or physical or organizational. It helps you see the structure underneath.